Is it working? Hello, do you hear me? Okay, great. Good evening, everybody. I'm Olga Soloveva from Frankfurt Institute, and today I will talk about applications to heavy ion collisions, and in particular influence of phase transition on transport properties of QCD matter. And my talk is not about lattice calculations. So first of all, I would tell you the motivation why we are using transport models. And as you can see here, the theoretical sketch of the QCD phase diagram, which was shown in many talks already. The most interesting part of this diagram is at finite temperature and baryon chemical potential is not yet explored by experiments, and it can be explored through heavy ion collisions. And in order to do so, we have to perform theoretical simulations which can describe dynamical evolution of heavy ion collisions. And in this matter, we have to quantify not only macroscopic properties of QCD matter at finite temperature and maybe, but also somehow relate them to microscopic structures, which is not which is notoriously difficult to do from first principles. Therefore, we have to rely to the effective models, phenomenological models. So in order to consider transport properties, we have to specify transport and microscopic properties and equation of state for the partonic phase. And there are different types of simulations of heavy ion collisions. Among them, now there are transport simulations, transport models with QGP phase. For example, there exists a Catania transport model where for the description of the partonic phase, they use a Quasiparticle model. While I belong to a group of Elena Bratkovskaya, and we use Parton hadron string dynamics dynamic model, which contain both hadronic and partonic phases. And for the partonic phases, it uses dynamical quasi-particle model. And here is our latest work on it. And as well, in description of partonic phase, the Polyakov number Yonah-Lazinian model is also used in IMPT transport approach. And however, there is also hybrid simulations. So in order to describe final observables, we cannot use just hydrodynamical evolution, but we have to combine them with hadronic models. So as you can see, unfortunately, we have to apply a lot of approximations in order to relate macroscopical properties, which can be evaluated on the lattice, to the microscopic properties such as cross-section, for example, or masses of quasi-particles. And today I will discuss in particular some results on the transport coefficients at finite temperature and maybe. And we will consider how the transport coefficients depends on the transition, which in the Polyakov number Yonah-Lazinian model have a critical endpoint at high maybe, and we consider as well a dynamical quasi-particle model. So today I will consider main transport coefficients, which is shear viscosity, bulk viscosity, and diffusion coefficients, which are appear in dissipative parts of T minimum, and the transport coefficients are required input for hydrodynamical simulations. And there is a problem that at finite temperature and baryon chemical potential, unfortunately, different model can have different predictions, while they can describe lattice data for equation of state quite well. And in order to consider wide range of baryon chemical potential, we will consider Polyakov extended non-Boolean-Lazini model, which allows for predictions of microscopic properties of QGP phase at finite temperature NMB. And at the same time, it enables us to evaluate quark-gluon plasma transport coefficients and wide range of baryon or chemical potential. So here you can see the phase diagram of this model, and the critical endpoint located at quite high quark chemical potential, which can be related to the baryon chemical potential. And the beauty of this model is that it has a chiral symmetry restoration. So the masses of quarks in this model dropping to bare masses at finite temperature. And also, Lagrangian of the model have the same symmetries as a QCD. And this model also contains gluonic degrees of freedom on the level of mean field and Polyakov loop effective potential. And all the parameters of the model can be fixed at finite temperature, at zero chemical potential. And we can predict the equation of state at non-zero baryon chemical potential. And in this particular work, which was made in collaboration with a group of York Aikelin, we have used extended Polyakov non-Boolean-Lazini model, which have several improvements. For example, it contains next to leading order contributions to the grand canonical potential, which can be seen as a meson contributions of mesons. And also the Polyakov loop effective potential was modified in order to have a presence of the quark quark-gluon interaction. So as I said already, you can see that Polyakov non-Boolean-Lazini have a good comparison at maybe equals 0 with the lattice equation of state. And at the same time, at high baryon chemical potential, it compares well with PQCD estimations of pressure. And we can relate our transport coefficients to the interaction rates of our degrees of freedom. And in that sense, we can estimate cross-sections of quark-antiquark interactions and evaluate, therefore, all the transport coefficients. And in Polyakov non-Boolean model, you can resum all the quark-antiquark loops in a random phase approximation, and it can be seen as a meson exchange, where the coupling constant, the coupling will depend on the mesons, so scalar, pseudoscalar. And in our case, we have also strange quarks, so we have strange mesons. And second important point, that in the case of Polyakov number Yanov-Lazini model, we are considering modified distribution functions, which contains Polyakov loop contributions. And it affects the distribution function at low temperature, while at high temperature, it equals to the Fermi distribution function. So at vanishing chemical potential, quark or baryon, we have seen, we evaluated specific shear viscosity and compared to various results from the literature. And we have found that shear viscosity, in agreement with other predictions, are increasing with temperature. And for finite chemical potential, we found that actually in the crossover region, the shear viscosity is increasing and the temperature dependence is quite the same. While approaching the critical endpoint, the temperature dependence in Polyakov number Yanov-Lazini model is changing drastically. And at high baryon chemical potential, here is μ equals 0.4 GeV, where it is first order phase transition in Polyakov number Yanov-Lazini model. The transport coefficients have different temperature dependence, so it's decreasing with scaled temperature. Here we depicted scale temperature T over Tc, because we will compare different model which can have different critical temperature, and this temperature as well varies with baryon chemical potentials. So we found actually that at zero chemical potential, our results are in a good agreement with other estimations and with estimations of dynamical quasi-particle model, which we will be seeing later. But important point here that we see the trend of increasing of values of specific shear viscosity. And other interesting transport coefficients is electric conductivity, which can be also related to the interaction rate in the same way. On other side, we can see that if we compare results of different models of scaled electric conductivity as a function of scaled temperature, we can see a difference in the value. While we see the same trend that the temperature dependence of scaled electric conductivity will change if we approach first order phase transition. So here you can see that the color corresponds different fixed quark chemical potential values. And what is interesting was to see that two different models, however, have a very similar increase with μb. So I showed you already the results from dynamical quasi-particle model, which is employed in PhD. And it described a strongly interactive quark-gluon plasma in terms of quasi-particles, which have Lorentzian spectrum function. So they have a resummed propagator, which have complex self-energies, while real part of self-energy is described by thermal mass of quasi-particles. The imaginary part corresponds to interaction widths. And these thermal masses and interaction widths are increasing with temperature and decreasing with baryon chemical potential in according to estimations from hard thermal loop. However, we don't perform resummations, so it's just phenomenological model where we fix our coupling constant in order to fit lattice equation of state. So in off-shell quasi-particle model, the entropy density can be estimated using the grand canonical potential. The grand canonical potential in propagator representation, and therefore the entropy density is related to the Coupling constant. So as I said before, we fixed our Coupling constant at 0 µb, and then in the crossover region, we performed some scaling hypotheses, which have shown us a very good comparison to the latest result from Wuppertal-Budapest collaboration. However, it's not a good approach to consider higher maybe value. So here, however, you can see that our results represents like lines on this plot, and the dots correspond to the latest data. We will consider later transport coefficients. So one of the advantages of quasi-particle model is that you can simultaneously evaluate transport properties of quasi-particles as well as equation of state. So, however, it also have some approximations, and here we evaluated specific shear viscosity or all transport coefficient using interaction rate, where we have considered leading order contributions from 2-to-2 scattering. And in the terms of quasi-particle model, if you consider effective Coupling constant, your transport coefficients will depend on the temperature and on µb. However, we have found that at finite temperature, we have very reasonable temperature dependence, which is in agreement with the predictions from lattice NF = 0 data and Bayesian analysis. And we see similar trend of increasing of specific shear viscosity, which is the ratio of shear viscosity to entropy density. And moreover, it is also very important to estimate other transport coefficients in order to check our consistency. And we have seen that also electric conductivity are in a good agreement with other predictions and with the predictions from the lattice. And moreover, we will continue to go to high maybe value. However, we can only interpolate their equation of state. So we present phenomenological model, which consists critical scaling from PNGL model. And it just interpolates equation of state. And in the framework of quasi-particle model, it also provides us the microscopical properties. So at finite small values of µb, we have good agreement with the latest data. And for high values of µb over T, we have reasonable agreement with the QCD results. So, and we implemented scaling using the same idea of relation of the Coupling constant to the entropy density, but we took in that time the entropy density from the PNGL model, which can be seen as a function of scale temperature. And therefore, we can obtain our Coupling constant, which enters all the microscopic properties. And here you can see our critical line. So the results which I show you will be relevant only for temperature higher than TC. So our we chose critical line in that way that it will go through the hot QCD and Wuppertal-Budapest collaborations data, but the location of critical point will be correspond to the PNGL µb. So, and another important feature which has been which should be checked is for maybe dependence is isentropic trajectories, that the model can reproduce focusing behavior of isentropic trajectories approaching the critical endpoint, which can be seen here. And also, we consider two setups of quark chemical potential that in our case, it approximates zero strangeness neutrality. And we've seen that trajectories for strangeness neutrality are shifted towards higher MEB, which is in accordance from the expectations from other models. And other important feature is the behavior of second derivatives of pressure, which in our case can be speed of sound and specific heat. And approaching the critical point from partonic side, the speed of sound is dropping to very small values, while specific heat is increasing. And you can see here that lines with different color correspond to the fixed MEB value, while at zero chemical potential, we have a good agreement with the estimations from the latest data. So, and as you can see here, this behavior can influence later the bulk viscosity. So the bulk viscosity approaching the critical endpoint from partonic side will increase in according to the decrease of speed of sound. However, the specific shear viscosity is not having the same increase because it's mainly depends on the interaction rate in our case. So, but this sudden rise of specific bulk viscosity is affected only by static critical exponent. So, and if we consider other transport coefficients or conductivity for conserved charges as electric charge and baryon charge, we will see that it's have the same trend as for PNGL model, and it also has a strong μB and μS dependence. So, but as I said to you, it's just quantitative results because we just interpolated our effective coupling constant in order to meet two asymptotics of high temperature and high μB. However, you can ask why do you need it? So we need it in order to consider dynamical evolution of QCD matter, which can be, as I mentioned earlier, produced in the Parton hadron string dynamics transport approach. And in this approach, is based on solution of off-shell transport equations, which is derived from Kadanoff-Boehm equations, and it has both hadronic and partonic phase. And as I said, it's very important to consider different descriptions of partonic phase. And in that sense, we have considered different setups for transport simulations where we consider temperature dependence or and maybe equals 0 and temperature dependence and maybe dependence of the cross sections and particle mass properties. So it is important to note that, however, one can relate the temperature and μB to the energy density and baryon density, which is taken into the transport approach. During the heavy ion collisions, we probe not only one baryon chemical potential, and even in the mid-drobidity, we probe the range of temperatures and baryon chemical potentials. So just slightly, I can summarize that after studying the basic bulk and flow observables, we've seen that we've seen small results of µB dependence. So, and we've seen that elliptic flow of strange particles are mostly affected by the properties of the quark-gluon plasma. So in conclusions, I have to say that we have seen influence of the order of the phase transition on the thermodynamic and the transport properties of partonic phase. And we've seen that actually the properties of partonic phase are very important for the future modeling of heavy ion collisions, and that we already can say that quantitative µB dependence can be seen in the final observables for strange particles. But the problem that in heavy ion collisions, high µB regions are probed at low bombarding energies, where the fractions of QGP is small. However, at high bombarding energies, the µB values are really small. So it is really hard to see any evidence of this influence of critical endpoint and first order phase transition. So thank you for your attention.
Thank you very much, Olga. Are there questions, comments?
Did I get it correct that you tuned the model for each temperature separately? For example, PNGL part, using the lattice data of the temperature variation of the whole physical quantities like pressure and so on?
No, it's
okay.
So the idea that we've seen that the scaling properties that we consider G squared.
Not this one. I'm talking about very early slides when you showed that.
This one?
Even before, you use some lattice thing. Yeah, this one. So parameters fixed at mu equal to 0.
This is a Polyakov Nambu-Lazini model, so it's just comparison to the latest results and to the QCD estimations at high µB.
So it's a comparison, not the input is. So the model has been fixed at t equal to 0 or something, right? Not
yes,
at each temperature.
Yes, but
okay.
The Polyakov potential has been fixed to the Young μ's at finite temperature. Yes.
Are there other questions? No, in the internet.
Thanks, Olga, for this very nice talk. At some point, I feel pessimistic now because it seems that we really need to compute things on the lattice, because you say that transport coefficient will depend a lot on the model, even if models seem okay. And so you would really need the transport coefficients from first principles, or no?
Yeah, that's a good point.
Optimistic.
So the models have a lot of approximations. They have the same trend, but the exact value will, of course, differs. But what we have seen that actually the difference in the transport coefficients will not influence a lot the final observables. So what we're doing, we can change our interactions in that sense that we can change the transport coefficients, and we will see how it will influence the final observables. But so far, it would be really beneficial to have calculations from first principles. So because it's just only models. So.
Can I comment also a little bit? Yes, to make it a little bit more optimistic and precisely advertise, we need lattice QCD calculations, because if you provide us only equation of state, we are trying to interpret it in terms of degrees of freedom and their properties. In this case, it's effective model with quasi-particles. However, we need to know about interactions and precisely about the properties of degrees of freedom from first principle. And this, up to now, you can provide us in terms of transport coefficients. And it's getting for effective models not so easy to get equation of state and the properties of degrees of freedom, which are defined by transport coefficients. And if you succeeded with that, like Olga presented here with dynamical quasi-particle model, you can realize that at least your properties which you subtract from that has some physical meaning. You can go ahead and perform heavy ion simulations using these properties and interactions, and then see the influence of observables. So, and the point is that if you want to go to larger baryon chemical potential, then unfortunately the fraction of QGP is getting smaller, and it's getting a little bit tough to see the effect so easily. But there is effect, and we found some observables which might be sensitive to that. So it's not so pessimistic, other way around.
It's also the question whether transport coefficients are the most evident for phase transition. I mean, you can think of fluctuations, for example, which may be more talking about really a phase transition, but that we have not explored.
So in some way, the transport coefficients are also the bridge between hydrodynamical simulations and transport, because in hydro it's input, and in transport it's it's our output. So and we can see that if we consider the same shear viscosity as, for example, in hybrid model, music plus URQMD, we have very similar results, and B manages can. So, but we are very interested in the results from first principle calculations. So, thank you.
Are there further questions? I don't see anything. So thank you very much. And last time, Olga.